Now it's my pleasure to introduce the next speaker. Evert is a PhD candidate in our group, propulsion and power at TU Delft. And the floor is yours, Evert.
Thank you. It's just the arrow, sorry. All right. Well, welcome everyone to my presentation. I'm honored to be here. It's my first SU2 conference. I'd like to thank you all for attending, and also special thanks to my supervisors, Dr. Pini, Nijso, and Daniel, who's joining online. So, yeah, as Pierre said, I'm a PhD at TU Delft. I'm doing a lot of work currently on combustion modeling in SU2, but today I'd like to talk a bit about a different topic. That's machine learning and artificial intelligence, which are taking the world by storm. This does not pose the end of humanity yet. So in the meantime, we can enjoy some of the benefits machine learning has to offer, such as self-driving cars and language recognition. Another topic where machine learning is gaining a lot of popularity is in the data-driven CFD. Now, what is data-driven CFD? It basically means that you replace your equation of state by a regression of reference data in order to model physics. An example of this is what I'm doing, combustion modeling using a generated manifold, where you're interpolating reference data to get your things like reaction rates, which are otherwise obtained in an expensive way. The current method, which is available in SU2 to do this, is a lookup table. Now, for relatively low dimension counts, this works very well. You just load your table into memory, you look up variables, and that's it. But if your problem becomes very complicated, your table dimensions will also rise, and this poses a memory problem, especially if you're also doing adjoint simulations. So an alternative method, which is well, rising in popularity as well, is the multi-layer perceptron, the MLP, or artificial neural network. The MLP has as an advantage that it's much more memory efficient and works with a variety of data compared to a lookup table, with the catch in that it's more difficult to construct. So in this presentation, I'd like to talk to you about some of the functionalities that I implemented into SU2 as how to evaluate and load these neural networks for your own uses. So yeah, I'll start with explaining a bit on how multi-layer perceptrons work in general and how the SU2 functionalities work. Then I'm going to talk about an application from my studies, and I'm going to close off with some of the ongoing work and expected improvements. So let me start by giving you a crash course in multi-layer perceptrons. So here on screen, you can see an example of a multi-layer perceptron. And this is basically an inspired mathematical structure inspired by biology, by our brains. The blue dots that you can see are the neurons or perceptrons, and they're all connected with the black lines that represent a certain weight. It's basically a very complicated function that you can express visually. The evaluation process starts with an input variable, which is a number. It's given to one of the two input variables. This input is multiplied by a weight and transported to the next neuron. This is then repeated for all the inputs until the next neuron, so you have a weighted sum. Then at that neuron, let me see if I can just do it with the mouse. Then at this neuron, a activation function is applied, so a small mathematical operation. And then the output of this neuron is then transported to the next neurons, and this is repeated throughout the network until you reach your output variable, and that's the overall output of the network. Now, the way that the weights that connect the neural network are determined is through training. So you give your network a bunch of reference data, you apply some gradient optimization, and that results in the architecture that represents your reference data the most closely. And the tool you can use for this is, for example, TensorFlow, but yeah, you also have tools like PyTorch, World Run It Over. So let's just say you have a trained neural network. It works really well, but you want to bring it into SU2. Now you can load this through Python wrapping, but this is very tedious to do and yeah, not very user friendly. So I opted for a different method, which I hope to standardize here. And that's through separate input files that describe the architecture and weights of the neural network. This allows for users to load dense feed-forward type multi-layer perceptrons, which are very popular and easy to use. You can load multiple MLPs at the same time. So you can have different MLPs represent different parts of your fluid model, for example. Currently, I'm still working in a private repository, but I hope to conceive a draft pull request soon, so it will be publicly available. So yeah, let me just briefly explain this input file, that explains the MLP architecture. The file contains information regarding the input variable names, normalization, as well as the weights. And the weights are distributed in a rather intuitive way with you can see they're grouped by layers. And yeah, they translate to each connection connecting the neuron of the previous layer to the next one in row and column order. Now, as I said, you can load multiple MLPs simultaneously. But how does SU2 exactly know on which MLP should be called when, especially if you have MLPs with some of the same inputs and outputs? Now, in that case, I implemented something that's called smart mapping, which basically circumvents the needs of hard coding, making it more user-friendly. Sorry, it's all a bit vague. It's probably because of the animations that I introduced here. Let's just say you have variables x1, x2, and x3, and you want to predict y1, y2, and the y3. But you have two MLPs loaded with the same, x1 to x3 as inputs and y1 to y4 as outputs. You can just hard code this into SU2, of course, but we don't want to do that. So the smart mapping algorithm automatically selects which inputs apply to which MLPs and which outputs have to be selected respectively. So you can predict your thermodynamic function with a single MLP or multiple MLPs. You don't have to change anything about the code itself. So let's talk about simulations. A nice application of this from my work, hydrogen combustion flame generated manifold. I'm currently working on the modeling of a laminar combustion through a flame generated manifold. Now, what is a flame generated manifold? You basically reduce your chemistry problem by grouping your transported scalars instead of being your species concentrations to something called a progress variable. This measures the state of the reaction. And then you interpolate your thermodynamic state through a lookup table, or in this case, a multi-layer perceptron. Now, in hydrogen combustion, there's a phenomenon called preferential diffusion, which makes the process a little bit more difficult. You need more transported scalars. So I'm working on making that simulation process more efficient. Transported scalars that I'm modeling here are the, set progress variable for measuring the state of the reaction, which is like the little letter y, enthalpy for modeling heat loss, and the mixture fraction for modeling preferential diffusion, which causes local changes in equivalence ratio. Again, this is very unfortunate. There is no text here. Basically, during the simulation, SU2 solves the fields for these three transport scalars. It accesses the manifold containing the reaction rate data and thermodynamic state data, and then gives that back to the SU2 solver. So in this part of the presentation, I'd like to make a comparison between the MLP and LUT regression methods, showing you some simulation results, as well as the computational performance comparison between the two, just to show that it's effective as well. All right. Again, this is, yeah, I'll skip this. So yeah, I'll skip this because this is not usable anymore. So yeah, this is the test case that I was using. This is a laminar burner geometry with incompressible flow at the inlet at an equivalence ratio of 0.5 in premix conditions with hydrogen, of course. The blue line here is a cooled wall set to a constant temperature of 300 Kelvin. So we're getting some nice heat losses here. And the flame front itself is initialized right here at the red line. So you will get a nice flame front formed right here. Yeah, I had the yeah, because now I cannot show the results. Basically, both, just trust me on this one. Both results were very similar between the lookup table and the multi-layer perceptron regression of the data set. There are no discernible differences apart from the passive species computation. So like measuring the emissions like nitrous oxide, there were some slight differences. And those were attributed to through the training of the multi-layer perceptron itself, where the reaction rate was slightly overestimated, which is well, up to me to improve the training in the future so we can use the MLPs more effectively. But nevertheless, for the rest, both of the results are very similar, but the computation time was also very much in line between the two methods, which is very good because MLPs are more computationally intensive than lookup table regression methods, while also being more memory efficient. So you're not sacrificing any computation time for a reduction in memory. So let me close off with talking about the ongoing work and the improvements to the method. The method compares very well to lookup table methods. Hopefully we can talk about that in the break a little bit. But I've not validated this yet with detailed chemistry results on a more complicated test case. So that's something that I hope to be able to do this year. I also like to add the ability to do gradient computation. That's something that you can analytically define through your MLP, but that code still has to be added to SU2, which will be very useful for things like sensitivity computations. We're working on application to other fields together with Matteo and our research group at TU Delft. We've already been able to apply to non-ideal computation of fluid dynamics, which worked out very well. Compressible, sorry. Yes. Also, well, speaking of gradient computation, the ability of being compatible with a joint will also be very nice for optimizing using data-driven CFD. And well, finally, get this code to the public through a tutorial on how to set up these input files, use the classes, and then well, draft a pull request so the code will be available publicly. All right, then this was a gift, but it's not running now. So thank you all very much for your attention.
Good job, Evert. Are there any questions?
Thanks to my name, Jacob. I'm curious in terms of like problems that can be efficient and but where you can see well, what's actually
So your question is about how to choose the correct architecture, you mean? Yes. Well, this is something that's not really part of this work. That's something that I did beforehand. The networks that I employed here were found through a hyperparameter search. I basically just ran a cloud of different architectures, combinations of different layer counts and neurons and activation functions, and generated a Pareto font based on computational performance, as well as the network size, because the larger your network, the more difficult it is to evaluate. So, and then the networks that I wanted to show here were the outcome from that parameter search. So unfortunately, there's no straightforward way to do this yet, but I will describe the exact process that I took in ongoing work.
So I think we have PowerPoint up if you wanted to. Yeah, maybe we have plenty of time. So take some questions, and if you want to animate your, let me hit play here, and then, but finish maybe taking the questions.
I'm Josh. I just wanted to know how much training data was required for building a.
Sorry, I did what?
How much training data was required for building a.
Yes, so the question is about how much training data was required to train these neural networks. The training data that I used was 1D combustion flamelet data, and I used the same data to generate the equivalent lookup table to make it fair. The number of flamelets that I used was in the around 5,000 or something, 5,000 flamelets. Which equates to about 1 million data points.
Question from Alberto.
Very nice presentation, thank you. I have two questions. One, how intrusive is this technique with respect to the form of SU2?
Right, so the question is, does this code interfere much with the rest of the architecture of SU2?
Yeah, change a lot.
Yeah. So no, mainly just an addition to the code. It's I put it in numerics. You can just, if you're defining your fluid model like a data-driven fluid model, you can just set up a new structure of the fluid model that just refers to those numeric structures. So like. For everything else in the code, nothing has changed apart from the addition of those MLP code structures.
And the other, maybe for assessing, if you have any technique to priori estimate the error, your model to be or your work on that.
So your question is on how to assess the accuracy of the MLP with respect to the lookup table.
Before running the.
Oh, before running it. No, I have not thought about that yet. That is, well, actually, like when I was generating these MLP architectures, I did. Like, of course, compare their validation scores, but I've not compared those for these architectures to the lookup table itself. But since the simulation results are very similar, it is you can deduce that the interpolation of things like density, temperature, and reaction rate are very closely approximated, but that's something that I'll have to verify. So, like here, we can see the solution field for the progress variable, and you can see, well, search for the differences, right? The flame length is approximated very closely. For enthalpy, there you can see that at the burner wall there is a very large drop, which is expected because that's a cooled surface, and those drops in enthalpy are also very similar between the two methods. Again, same story for mixture fraction and temperature as well. So the temperature is directly interpolated from the lookup table and the MLP. And because they're so similar here, it goes to show that they're very similar in accuracy. For the passive species, the emissions, we start to see some differences. You can see right here that the lookup table has a little bit more emissions in this area. But for the NO, there's a clear difference. So here you can see that the local emissions for NO are much higher for the MLP than for the LUT. And that's because of the overestimation of the reaction rate of NO in this area. So that MLP requires a little bit more training or a slightly different architecture.
Okay. Tom, you have a question?
Yeah, I have a question. So you mentioned adjoint methods at the end, and I'm wondering how you plan to differentiate through the MLP.
So there are two methods, just to repeat it. The question is about how to approximate the gradients through the MLP. And I have two methods in mind. First is to well, basically just let algorithmic differentiation do the work, which will of course require more memory to do, but is a little bit less intrusive. The other way is to let the MLP itself compute the gradients analytically. So you can just write them down analytically, store the derivative of the activation functions, and that way compute the derivative of the outputs with respect to the inputs and feed those to the adjoint instead. So those are two methods I have in mind, and would like to compare those in terms of accuracy and computational requirements.
Thank you. Are there more questions? We were a bit ahead of time, so if there are more questions, there are still 3 minutes before the end.
Did you want to show the other, now that we have the
that's
animations up, sure you wanted to show a couple more things?
Yeah, just to show the solution process a bit on this Combustion FGM solver. So, well, right there we have the governing scalar equations that are solved by SU2 throughout the domain. And here we have the fluid model structure for the flamelet solver. So during every iteration, SU2 gives the progress variable enthalpy and mixture fraction to the fluid model. Then within this fluid model, I have 3 MLPs loaded. The first one is used for the thermodynamic state interpolation. So this one returns the temperature, density, CP, dynamic viscosity, and conductivity based on the progress variable enthalpy and mixture fraction. And right here you can see the network architecture that was found through hyperparameter search. The second MLP was used to interpolate the reaction source terms. These are kind of pesky terms. They are very nonlinear and have a lot of bumps. So the network architecture for this one is a little bit bigger. It contains more neurons. And the final network architecture interpolates the preferential diffusion scalars according to the model devised by Nijso and colleagues. And these terms basically generate the local variances in equivalence ratio that occur in hydrogen combustion. And then for the lookup table, it's all a little bit more simple. All the data is stored in the same quasi 3D lookup table, which was set up as a stack of 2D trapezoidal maps in the mixture fraction direction. So yeah, that was those are all the relevant animations that I wanted to show. Again, apologies for not making the presentation compatible with the PDF in that regard. There's a nice little animation.
Oh, that's good.